So let's look at vectors in R2 and R3. So what is a vector? It's a set of instructions on how to move by giving two pieces of information, a direction and a distance. So anytime you communicate a direction and a distance, you're giving me a vector. So let's do some examples. So let's write down some vectors. What if I say, go 5 miles northwest? That's a vector. I'm giving you a direction, northwest. I'm giving you a distance, 5 miles. That's a vector. Here's another vector. Let's say I'm in R3, and I say go A units in the X direction, B units in the Y direction, and C units in the Z direction. So if I'm in R3, I take A steps in the X direction, B in the Y, and C in the Z direction. That's a vector. I'm giving you direction and distance. Now this vector, if I'm in R3, is such a common set of instructions that we have special notation for it. We give an angled bracket, A, B, C. So this means A units in the X, B in the Y, C in the Z direction. Let me give you an example of something that's not a vector to contrast it with what a vector really is. So here's something that's not a vector. If I say, go to Disneyland, that's not a vector because I'm not giving you a direction or a distance. If I say go to Disneyland, this set of instructions depends on your current location. However, if I say go 5 miles northwest, that's instructions that are position independent. I don't care if you're in San Luis Obispo or San Diego, go 5 miles northwest gives you direction and distance. However, go to Disneyland depends on your current location. That doesn't count as a vector. Okay, so let's define the length of a vector. So the length of a vector v, and when we write down vectors in general, we'll put a little bar over the symbol v to help us remember we're actually talking about instructions that give a direction and a distance, not just a point in space. So the length of a vector v, let's say I'm in R3, is given by writing down the vector with these two absolute value looking bars around it, but it's not absolute value. This is actually the length of vector, giving you the distance traveled. This is, let's say, my vector A, B, C in R3. The length is just given by the distance formula, A squared plus B squared plus C squared. Because if you're standing at 0, 0, 0, and you follow these instructions, this is how far you've actually moved. If I'm in R2, instead of R3, then the length of the vector v, this time I might only have two components, A, B. That would again be the square root of A squared plus B squared. That's if I'm in R2. Okay, we can graphically depict vectors. So vectors in R2 or R3 can be drawn. Let me give you an example. So what about the vector v? Let's say it's the vector 1, 2. That's a vector in R2. This can be drawn. So I'll draw a picture of the vector 1, 2 in R2. There's 1, 2, 3, 4, 5. 1, 2, 3. There's -1. So let's say I happen to be standing at 0, 0. If I happen to be at position 0, 0, the vector 1, 2 says, take 1 step in the x direction and 2 steps in the y direction, landing here. So I could draw an arrow that starts at 0, 0 and ends at 1, 2. This arrow points me in the direction that I need to move. This arrow gives a direction and it gives me a distance, a length. That's if I'm standing at 0, 0. If I happen to be at a different coordinate, like let's say I'm starting at the position 3, 1, this vector still tells me to take 1 step to the right and 2 steps up, giving me this picture. Both of these vectors are the vectors 1, 2, because these vectors are position independent. It doesn't matter where my current location is, if I'm even down here. The vector just tells me a direction and a distance. All of these are the same exact vector. Because it doesn't matter where you start drawing your vector, usually, unless otherwise stated, we'll start drawing our vector at 0, 0 just to put our pictures right in the middle of the coordinate plane. Okay, now vectors can be added together and they could be multiplied by constants. So vectors can be added together. Let me do an example of adding 2 vectors together. So what if I said, move 5 miles east? That's a vector. It gives a direction and a distance. And then what if I added that to the vector, go 10 miles north? Another vector. When you add 2 vectors, what you're saying is, do the first set of instructions, and then when you're done with that, follow the next set of instructions. So you do one after the other. That's just vector addition. So here's another example. The vectors, let's see here, 1, -1, plus 2, 2. This would say, start by moving in the plane R2 using this set of instructions, and then once you're done with that, follow this set of instructions. Here, let me draw a picture of this last one. So it says, maybe you're starting at 0, 0. Travel in this direction. Take 1 step to the right and 1 step down. So first vector is here. Then, once you're done with that, take 2 steps to the right and 2 steps up. So 2 steps to the right and 2 steps up. Okay, so now I'm over here. If I add these 2 vectors together, I follow one set of instructions and then the next, I landed at the point 3, 1. So the net effect of following these 2 instructions one after the other is that I get the vector 3, 1. In total, I moved 3 steps to the right and 1 up. You can get that just by adding the components together. So just by adding components, you can add 2 vectors. There's also something called a vector scalar multiplication. So let me finish the video by discussing scalar multiplication. So vectors can be scaled or multiplied by constants. They cannot be, two vectors cannot be multiplied together, but you could take a vector and multiply by a number, a constant. So for example, if I do 2 times the vector, move 2 steps to the right, multiplying by 2 means to go twice as far as before. So go in the same direction. So when I multiply by a constant like 2, the direction is going to stay the same. The only thing I'm going to do is scale, multiply how far I move. So if I do 2 times move 2 steps to the right, this is the same as a vector move 4 steps to the right. Here's another example. What if I did 3 times the vector 1, 1, 1? So here's my vector in R3. If I do 3 times this vector, I go in the same direction 1, 1, 1, just 3 times as far. So this would be the vector 3, 3, 3. One more example. I could even scale by a negative. If I scale by a negative, like let's say I have the vector 3, 2, then I get the vector negative 15, negative 10. This multiplication by a negative rotates the vector 180 degrees, and now I'm going in the exact opposite direction that I did before. Now, a key observation about vectors multiplied by constants is that when I multiply a vector by the constant, the two vectors are parallel. The direction is the same, only the length could be different. Okay, great.